Hello everyone. Today I will discuss characteristic equation, eigenvalue problem and Cayley-Hamilton theorem, which are basically algebra or you can say linear algebra. Characteristic equation, eigenvalue problem, Cayley-Hamilton theorem are practically important and practical problems from linear algebra. Okay. In general, in my video tutorials, I discuss mainly concept and then I go through few examples. But in this topic, I just define what is characteristic equation, what is eigenvalue problem, and what is the statement of Cayley-Hamilton theorem. Then I will go to the problems related with these topics. Because in this topic, problems are very much important rather than the theorems or the statements. Okay, so let's start. What is characteristic equation? That is our first topic, characteristic equation. Let capital A be a n by n matrix. Okay, let capital A be a n by n matrix. Means the matrix should be a square matrix over a field capital F, so that capital A equals to A11, A12, A13 dot 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 A1n, A21, A22, A23 dot 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 A2n, and last row is an1, an2, an3 dot 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 ann. That is n row and n columns. Means characteristic equation or eigenvalue problem or Cayley-Hamilton theorem, we have to consider only square matrix. Then determinant of A minus xin. Here in means the identity matrix with the same order as of capital A. Then the determinant A minus xin is said to be the characteristic polynomial. Determinant A minus xin is said to be the characteristic polynomial of capital A and is denoted by psi of capital A x. Psi of capital A x. Okay, this is psi of capital A x. Means characteristic polynomial is denoted by psi of capital A x. All right. Okay. So determinant of A minus xin is what? Determinant of A minus xin is determinant of A means this matrix minus x, in means 1, 1, 2, 2, 3, 3 and so on, right? So if we do simplification this part, we basically will get A11 minus x, then A12, A13 dot 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 A1n, A21, A22 minus x, A23 dot 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 A2n, A31, A32, A33 minus x dot 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 A3n, and last row is an1, an2 dot 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 an minus x. Means here x will be subtracted from the diagonal elements only. From the diagonal elements only, because in is what? Because in is a identity matrix like this 1, 0, 0, so on, then 0, 1, 0, so on, then 0, 0, 0, dot dot dot, last is 1. Okay, so if we do subtraction, we will be, the determinant will be like this, a11 minus x, a12, a13 dot 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 a1n, a21, a22 minus x, a23, a2n and so on. So this is our characteristic polynomial. Now if we do equating with 0, means characteristic polynomial equals to 0, then we will get an equation. That equation is called characteristic equation. Okay, that equation is called characteristic equation. Okay, the equation psi ax equals to 0 is said to be the characteristic equation of A. So what we get? We get first characteristic polynomial. Characteristic polynomial is determinant of A minus xin. Then that is equals to 0 will give us an equation which is known as characteristic equation. Okay. Now the degree of the characteristic equation is same as the order of the matrix capital A. It is obvious. and the coefficients are scalars belonging to capital F. Now come to the very important topic, that is Cayley-Hamilton theorem. What Cayley-Hamilton theorem states? It states that every square matrix satisfies its own characteristic equation. Okay, if capital A be an n by n matrix and the characteristic polynomial of capital A B, means if we do simplification this polynomial, after simplification the polynomial will be like this: c naught x to the power n plus c1 x to the power n minus 1 plus c2 x to the power n minus 2 plus dot 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 plus cn, that is equals to 0. This is characteristic polynomial. Then capital A should satisfy this polynomial, means in place of x we have to write a. Okay, in place of x we have to write a, or we can write a like this: c naught a to the power n plus c1 a to the power n minus 1 plus c2 a to the power n minus 2 plus dot 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 plus cn. Actually here it is empty, right? But we cannot do here empty because this is an equation of matrix. Here this is matrix, this is matrix, this is matrix, so we have to put here some matrix. So here we have to put identity matrix In, that is equals to 0 matrix of the same order of A, right? So this is Cayley-Hamilton theorem. In the next few examples I will discuss how we solve few problems with the help of Cayley-Hamilton theorem. So Cayley-Hamilton states that every square matrix satisfies its own characteristic equation. Okay, means in place of x we have to put a square matrix. Okay, now what is eigenvalue of a matrix? Eigenvalue, a root of the characteristic equation of a square matrix capital A is said to be eigenvalue, or a characteristic value of capital A. A root of the characteristic equation means we get characteristic equation, then we have to solve the equation. If we solve the equation we get few roots. These roots are called eigenvalues of the given matrix. Okay, the roots are called eigenvalues of the given matrix. And definitely the number of eigenvalues is equal to the order of the matrix, because the number or order of the matrix equals to order of the equation, and we know order of the equation equals to number of roots. So definitely number of roots equals to order of the matrix. Now eigenvector. What is eigenvector? Let capital A be a n by n matrix over a field F. A non-null or non-empty or non-void vector capital X belonging to V and F is said to be an eigenvector or a characteristic vector of A if there exists a scalar lambda belonging to F such that Ax equals to lambda x. Here actually x is the eigenvector. If x satisfies this condition, Ax equals to lambda x. I am repeating, if x satisfies this condition, Ax equals to lambda x, then we can say that x is the eigenvector of the matrix capital A. Now let's start few examples, and when I will start examples I will define these eigenvectors more precisely. Okay, so our first example is find the eigenvalues of the matrix. This is a 3 by 3 order matrix, right? So let capital A equals to 1 minus 1 0 1 2 minus 1 3 2 minus 1. The characteristic equation of capital A is determinant A minus lambda I3 equals to 0. Characteristic equation. Now after simplification we will get, just do subtraction from the diagonal elements. Okay, that is 1 minus lambda minus 1 0 1 2 minus lambda minus 1 3 2 minus 2 minus lambda equals to 0. Now we have to simplify this, or we have to just open the determinant to get the values of lambda. Here the values of lambda are 1 1 and minus 1, means all the values of lambda are real numbers. Okay, hence the required eigenvalues of capital A are 1 1 minus 1, because the roots of the characteristic equation are known as characteristic value or eigenvalue of the given matrix capital A, right? As we know in our definition, what is eigenvalue? Eigenvalue are the roots of the characteristic equation. So this is our characteristic equation, and the roots are 1 1 minus 1, so we can say 1 1 minus 1 are the eigenvalues or characteristic value of the given matrix capital A. Alright, next question, example number 2. Find the eigenvalues of the matrix 0 minus 1 1 0. Let capital A equals to 0 minus 1 1 0. Therefore the characteristic equation of capital A is determinant A minus lambda I2. Here I have taken I2 because this is a 2 by 2 order matrix. Okay, but before I was taken I3 because the given matrix was 3 by 3 order matrix. So here determinant A minus lambda I2 equals to 0. Again diagonal 0 minus lambda minus 1 1 0 minus lambda equals to 0. Just to do simplification, here what I get lambda equals to plus minus square root of minus 1, and we know square root of minus 1 is iota, right? Square root of minus 1 is iota, so lambda is plus minus I. So here we say that the values of lambda are not real, so it may be possible that all the roots of the given characteristic polynomial may not be real. Then also we can write the required eigenvalues of capital A are I and minus I. I and what? Minus I. Means whether the roots are real or imaginary numbers, the roots are only the characteristic or the eigenvalues or characteristic value of the given matrix capital A. Next, we have to find eigenvectors. In the previous two examples, I have shown how we can find eigenvalues. Now come to eigenvectors. Find the eigenvalue and the corresponding eigenvectors of capital A. Same example only, just same example 0 minus 1 1 0. Same example is taken here. So do the same process to find the values of lambda. Here lambda again plus minus I. We did this here. So just do the same way, we'll get the values of lambda as plus I and minus I. So the eigenvalues of capital A are I and minus I, but these are not real. So if the eigenvalues are not real, then what will we do? Here we have to remember these two things. First is, if capital A be a real matrix and the eigenvalues of capital A are not real, and the eigenvalues of capital A are not real, this is very much important, the eigenvalues of capital A are not real, then A has no eigenvector. Then A has no eigenvector. Okay, get my point? If capital A be a real matrix, okay, and the eigenvalues or characteristic values of capital A are not real, like this problem, then we say that the eigenvalues does not exist. But if we consider capital A as a complex matrix, then the eigenvectors of capital A corresponding to the eigenvalues can be obtained as complex numbers. And remember one thing, the real eigenvalues will provide us real eigenvectors, and the imaginary eigenvalues or imaginary characteristic values will provide us imaginary or complex eigenvectors. Okay, so let capital X equals to x1 x2, means 2 row 1 column, be an eigenvector corresponding to I. Actually we always take 1 column matrix, but the number of rows will be equal to the order of the matrix. Here the given matrix is of 2 order or second order matrix, so number of rows is 2. If the given matrix is of third order, then we have to consider 3 rows but 1 column, so a column is 1 only. Okay, so let capital X equals to x1 x2 be an eigenvector corresponding to I. So we have to find the values of x1 and x2. So this is our condition of eigenvectors, right? Because ax equals to lambda x. If x satisfies this condition, then we can say that x is the eigenvector. Here lambda is what? Here lambda is I. So x equals to ix. Now put the values of a. A is 0, minus 1, 1, 0. X is x1, x2 according to our assumption. lambda is I and x is x1 x2. Then do the multiplication row into column method, that is matrix multiplication method. 0 into x1 plus minus 1 into x2, that is minus x2. 1 into x1 plus 0 into x2, that is x1, equals to ix1 into ix2. Then do the comparison. What we get? Minus x2 equals to ix1 and x1 equals to ix2. After simplification, we see that actually these equations are equivalent equations. Okay, they are same. So we have one equation with two variables. So number of solutions definitely infinity. So let us consider x2 as k1. What is k1? K1 is a non-zero complex number. This is also very much important. Whenever we consider any constant or whenever we consider any number like this, if the eigenvalue is real number, then we have to consider the constant as a real number, non-zero real number. But if the eigenvalue is imaginary or complex number, then the scalar is also non-zero scalar number, complex number. Okay. So if x2 equals to x1, then x1 will be I into k1. Okay. So what is x1, x2? x1 is our I k1 and x2 is only k1. Taking k1 common, we have I comma 1. So this is our x1, x2. So what is the matrix? The matrix is x equals to x1, x2 like this. So just write down k1, I1, where k is a non-zero complex number. You have to write this like this way only. Okay, where k1 is a non-zero complex number, again I am repeating, if eigenvalue is real, we have to write where k1 is a non-zero real number. If eigenvalue is complex number, then we have to write k1 is a non-zero complex number. Also, I told you that if eigenvalues are real, then the eigenvector will be real. If eigenvalues are complex, then the eigenvector will be complex number. So see, this is complex matrix only. Again, for lambda equals to minus I, we do the same thing. Okay, and we get x2 equals to ix1. The equations are equivalent, so let x1 equals to k2. So x2 is I into k2, where k2 is non-zero real number. Here you have to write k2 not equals to 0. Okay. So what are the values of x1, x2? x1 is our k2 and x2 is I k2. Hence the required eigenvector of a capital A corresponding to lambda equals to minus I is k2, I k2, k2 common, 1 comma I, where k2 is a non-zero complex number. So this is the process. Okay. So this is one vector or eigenvector corresponding to minus I, and this is one eigenvector corresponding to eigenvalue I. Now come to the fourth number question. Find the eigenvalues and the corresponding eigenvectors of the real matrix. The before one was 2 by 2 order matrix. Now this is 3 by 3 order matrix, but process is same only. The characteristic equation of capital A is determinant A minus lambda I3 equals to 0. Then do the subtraction from the diagonal elements. After simplification, do this in your, okay, I know you can solve this. So values of lambda are 1, 1, 5. Okay, 1, 1, 5. So the eigenvalues of capital A are 1, 1, 5. Here you see all the eigenvalues are real numbers. So definitely it will provide us real eigenvectors. Also, you see that two eigenvalues are equal. Okay, this is quite interesting when we get equal eigenvalues. Let capital X equals to x1, x2, x3 be an eigenvector corresponding to lambda equals to 1. Then by the definition Ax equals to lambda x, just putting values of A, Ax, lambda is 1, x. Then do the do the matrix multiplication row into column method. And after simplification, what we get? x1 plus 2x2 plus x3 equals to 0. Again x1 plus 2x2 plus x3 equals to 0. Then x1 plus 2x2 plus x3 equals to 0. Now number of equation is 3. Number of equation is 3. but these three equations are equivalent, or you can say equal actually. So these are nothing but actually just one equation, but the number of variables is 3 only. So 3 variable, 1 equation. So infinite number of solutions exist other than 0, 0, 0, right? Now we can write x1 plus 2x2 plus x3 equals to 0 like this way, x1 equals to minus 2x2 minus x3. Or you can write like this, 2x2 equals to minus x1 minus x3, or x3 equals to minus 2x2 minus x1. It is your own choice, but I have written here x1 equals to minus 2x2 minus x3. So let x2 equals to this, x2 equals to c, alright, and x3 equals to d, where c and d are non-zero real numbers. Alright, just remember real number, because here lambda is 1, which is nothing but a real number. So x1 is what? Minus 2c minus d. Now come to the solution, x1, x2, x3 equals to minus 2x2 minus x3, comma, x2 is x2 only, x3 is x3 only. So minus 2c minus d, this is this one, minus 2c minus d, comma, x2 is c, x2 is c, and x3 is d. Okay, then we have to splitting them, and we will get minus 2c comma c comma 0 plus minus d comma 0 comma d, taking c common, minus 2 1 0 and d minus 1 0 1. Now if we see carefully, we see that this and these are actually linearly independent, because we cannot express them like this, alpha equals to some constant into beta. We cannot express like this way these two numbers, or these two elements, or these two vectors. Okay, so we say that these vectors are linearly independent, right? So what is x1 x2 x3? x1 x2 x3 is equals to c. Come to the assumption, x is x1 x2 x3. Now x1 x2 x3, the values of x1 x2 x3s are, x1 is c minus 2 1 0 minus 2 1 0 plus d minus 1 0 1, where c and d are non-zero real numbers. But if eigen value is complex number, then we have to write c, d are non-zero complex numbers. So you see, when we have equal eigenvalues, the eigenvector corresponding to that is like this. If one is an eigenvalue of capital A of multiplicity 3, then the result will be c this plus d this plus another constant e into this. Okay. Now next, here lambda equals to 5, that is the next eigenvalue, and according to definition x equals to lambda x. So do the simplification, you do this in your own. We get these three equations, Now we see these three equations are actually not equal, okay, but these are homogeneous equation, and homogeneous equation is always consistent, because 0 is there at least one root, but we have to find non-zero solution. Okay, actually eigenvectors are always non-zero solution of the system. So to find the non-zero solution, we have to consider any two equations out of these three equations. Here I have considered the first two equations. Okay, so by simplifying or by cross multiplication, what I get x1 by 4 equals to x2 by 4 equals to x3 by 4. Then dividing all this 4 by 4, we get x1 by 1 equals to x2 by 1 equals to x3 by 1 equals to k. Now what is k? K is a non-zero real number, because lambda is 5, which is a real number. Now if I put x1 x2 x3 here, we get k equals to 0, but we have to consider k as non-zero real number. So the result will be x1 x2 x3 is k k k, taking k common 1 1 1. Now come to this, here 1 1 1, exactly one number or one element or one vector, and definitely one vector are always linearly independent, right? So the result or eigenvector is x1 x2 x3 equals to k 1 1 1, where k is a non-zero real number. Hence, required eigenvectors of capital A corresponding to eigenvalue lambda equals to 1 is this, where c and d are non-zero real numbers, and corresponding to the eigenvector lambda equals to 5 is this, where k is a non-zero real number. Now come to the next problem, which is the application of Cayley-Hamilton theorem. Actually, Cayley-Hamilton theorem is quite interesting because by the help of Cayley-Hamilton theorem we can do few interesting problems. Here we have to find A inverse by the help of Cayley-Hamilton theorem. Now see how we can do this. Here use Cayley-Hamilton theorem for the matrix capital A to find A inverse. Here A equals to 0, 0, 1, 3, 1, 0, minus 2, 1, 4. So the characteristic equation of capital A is determinant. This is not mod, okay, this is determinant. Determinant A minus lambda I3 because this is third order matrix equals to 0. Then just do subtraction from the diagonal elements, that is 0 minus lambda. Okay, 0 minus lambda, 0, 1, 3, 1 minus lambda, 0, minus 2, 1, 4 minus lambda equals to 0. Then do the simplification, okay, and what we get, lambda cube minus 5 lambda square plus 6 lambda minus 5 equals to 0. See, this is a cubic equation because the order of the matrix is 3 and definitely the characteristic equation is the same order as of the matrix capital A. Since by Cayley-Hamilton theorem we know that every square matrix satisfies its own characteristic equation, means we can say capital A will satisfy this equation, means in place of lambda we can write A. Okay, so according to the statement or theorem we can write A cube minus 5A square plus 6A minus 5 I3. We cannot write here anything else. We have to write here I3, identity matrix equals to 0, 3, third order 0 matrix. Okay, like this, A cube minus 5A square plus 6A minus 5I3 equals to 0, 3. Then multiplying both sides by A inverse, the result will be A inverse A cube minus 5 A inverse A square plus 6 A inverse A minus 5 A inverse I3 equals to A inverse into 0, 3, means third order 0 matrix, it will be 0 matrix only. Now this will give us A square because we know A inverse A equals to I. Minus 5 A inverse A square is A only, plus 6 A inverse A is I3, minus 5 A inverse I3 is A inverse equals to 0. Now taking this in one side and transpose all the remaining, we'll have minus 5A inverse equals to 0 minus A2 plus 5A minus 6I3. That is A inverse is minus 1 by 5 within bracket minus A square plus 5A minus 6I3. Then just taking minus common or just multiplying with the inner terms, we will get 1 by 5 A square minus 5A plus 6I3. So this is our A inverse. Now we have to put the values of A square, A and I3 and then do simplification, then we'll get A inverse. How? Just see, A inverse equals to 1 by 5 A square means A into A minus 5A plus 6I is third order identity matrix like this. Then do the matrix multiplication method, that is row into column method. Row into column method means 0 into 0 plus 0 into 3 plus 1 into minus 2, that is minus 2, then 1, 4. Okay, just do this in your own. I know you can do this because we have already know how to do matrix multiplication, how can we multiply determinant, how can we simplify determinant, etc. So what we have finally 1 by 5 and after simplification we'll get 1 by 5, 4, 1, minus 1, 3 minus 15 minus 12, this is 2, this is 3, minus 5 plus 10 is 5, this is 0 and this is 0. Okay, so this is our A inverse. Okay, this is our A inverse. So see, by the help of Cayley-Hamilton theorem we can easily find A inverse. Next question is, this is also important question because in this problem I will show how we can use Cayley-Hamilton theorem and mathematical induction method together to solve this type of problem. Okay, quite interesting problem. If capital A equals to 1, 0, 0, 1, 0, 1, 0, 1, 0, show that for every integer n greater than equal 3, a to the power n equals to a to the power n minus 2 plus a square minus I, hence evaluate a to the power 50. So here capital A equals to this given. The characteristic equation of capital A is determinant A minus lambda I3 equals to 0. Then do this. The characteristic equation is lambda cube minus lambda square minus lambda plus 1 equals to 0. Alright. And we know by Cayley-Hamilton theorem every square matrix satisfies its own characteristic equation. So we can write A cube minus A square minus A plus I3 equals to 0, 3, third order 0 matrix. That is, we can write A cube equals to A square plus A minus I3 by doing transpose. Now see, our formula was a to the power n equals to a to the power n minus 2 plus a square minus I. That is, a square and minus I is constant or fixed, you can say, and these two numbers or these two matrices are just variables. Actually their powers are variables. You see here 3, here the power is 3 minus 2, that is 1. Alright, say this is alright. A to the power 3, here a square plus a to the power 3 minus 2, that is 1, or a to the power 1, you can say. So the formula a to the power n equals to a to the power n minus 2, a to the power n minus 2 means this term here, then a square, this, and minus I. Holds for n equals to 3, right? Means if we take n equals to 3, the result is true. Also it is given the result is true for n equal to 3 and more than 3. So we see that the result is true for n equals to 3. Now we can write by mathematical induction, or we can assume by mathematical induction that the result is true for n equals to m, where m is greater than 3, because we already know that the result is true for n equals to 3. So by mathematical induction we can write a to the power m equals to a to the power m minus 2 plus a square minus I. Okay, then we have to show that if the result is true for n equals to m, then the result will be true for n equals to m plus 1. So do by multiplying equation number 2 by capital A, we obtain a to the power m plus 1 equals to a to the power m minus 2 into a, that is a to the power m minus 1. Here a to the power m plus 1, a to the power m plus 1 equals to a to the power m minus 1 plus a cube minus a. Just multiplying equation number 2 by capital A or matrix A. Now we have to replace this a cube by this value a square plus a minus I3. We have to replace a cube by this value, your equation number 1 by 1. Then we will have a to the power m minus 1 plus a square plus a minus I, and minus a is already here, so it is here minus a. This minus a plus a will be eliminated, then the result will be a to the power m minus 1 plus a square minus I. Now you see that the result is true for n equals to m plus 1 provided the result is true for n equals to m. But the formula holds for n equals to 3. So by mathematical induction we can say that the result is true for n equals to 3 plus 1 equals to 4, 4 plus 1 equals to 5, 5 plus 1 equals to 6, and so on. That is, by mathematical induction we can say the result is true for any value greater than or equal to 3, right? Hence a to the power n equals to a to the power n minus 2 plus a minus I is true for all n greater than or equal to 3. So this is the proof of the first part, which is done by mathematical induction. Now we have to find a to the power 50. This is we do by symmetry method. You see, we have this result a to the power n equals to a to the power n minus 2 plus a minus I. So a square is what? A square will be a to the power 2 minus 2, okay, plus a minus I. A to the power 2 minus 2 means a to the power 0, that is 0 only. Okay, just forget it. A square is a into a. A square is a into a, right? A square is a into a, then do the matrix multiplication, we have this result. Now we have to use this statement here. A to the power 4 is what? A to the power 4 is a to the power 4 is a to the power 4 minus 2 plus a minus I. A to the power 4 minus 2 is 2, that is a square plus a square minus I, sorry, here 2 will be, okay. A to the power 4 is a to the power 4 minus 2 plus a square minus I, because here n is 4. The result is a square plus a square minus I. A square plus a square is actually 2a square, whatever. We have the value of a square already, that is a square is 100, 110, 101, plus again a square is 100, 110, 101 minus identity matrix of third order like this. Then do the simplification. 1 plus 1 is 2, 2 minus 1 is 1, 0, 0, 0, 0. Then 1 plus 1 minus 0, that is 2. 1 plus 1 minus 1 is 1, 0 plus 0 minus 0, 0. Okay, so this is our a to the power 4. Then we have to find a to the power 6. A to the power 6 is a to the power n minus 2, means 6 minus 2 plus a square minus I. That is a to the power 4 plus a square minus I. Okay, now what is the value of a square? A square is this. We have to put here a square, and we have to put here a to the power 4 because we know the value of a to the power 4. A to the power 4 is this. Then we have to put the value of a square. A square is this value. this is a square, minus I is identity matrix, then again do the simplification, we get this result. Okay, now if we see carefully, we see that if it is 6, then here 1 0 0 0 1 0 1, this is 3 3, these two elements are 3 3, means half of this power. Come here, here it is power say 4, and here it is 2 2, remaining are same, okay, remaining are same. Just see, this is 3 3, this is 2 2, and remaining are same. So when the power is 6, here 3 3 means half of 6. When the power is 4, it is half of 4, that is 2 2. When the power is 2, it is half of 2, that is 1 1, and remaining are same. So by symmetry we can say, if it is a to the power 50, then it will be 25, it will be 25, and the remaining will be same. Hence from the symmetry we can write a to the power 50 is 1 0 0, half, that is 25 1 0, or 25 0 1. Okay, so this is our result. So come to the last problem, and this problem is very much important regarding your exam purpose. Actually, in my previous examples I have shown you that if the matrix is given, then we can find eigenvector by the help of eigen characteristic equation, eigenvalue, then eigenvector. But in the last problem, this is our last problem of this video, that here eigenvectors are given and we have to find matrix. Okay, actually from matrix we can find eigenvectors, but in the last example eigenvectors are given, we have to find the matrix. See, capital A is a 3 by 3 real matrix having the eigenvalues 2 3 1, with 1 2 1 0 1 1 1 1 1 are the eigenvectors of capital A corresponding to the eigenvalues 2 3 1. Means this is the eigenvector corresponding to 2, this is the eigenvector corresponding to 3, and this is the eigenvector corresponding to 1. Okay, find the matrix capital A. So let x1 equals to 1 2 1, x2 equals to 0 1 1, and x3 equals to 1 1 1. Let us assume this. Then by definition we know that ax equals to lambda x. For the first vector we see lambda is 2, so definitely ax1 equals to 2x1, then x1 equals to 2, because we don't know value of a, so just write down ax1 equals to 2, x1 is 1 to 1, so 2 into 2, 2 into 2 4, and 2 into 1 is 2, the result is 2 4 2. Then do ax2 equals to 3x2, x2 equals to 3, x2 is 0 1 1, the result is 0 3 3, and last one ax3 equals to 1 into 3, last eigen value, that is x3 equals to 1 1 1 1, that is 1 1 1 only. So we have ax1, we have ax2, we have ax3. ax1 is this, ax2 is this, and ax3 is this. Let P be the matrix with eigenvectors only. Okay, eigenvectors means this, then this, then this. All right, eigenvectors only, this 1 2 1 0 1 1 1 1 1, and we consider AP by taking this 2 4 2 2 4 2, then 0 3 3, then 1 1 1. Okay, this is our AP, because these are ax1 ax2 ax3 which provides us AP, and P provides us eigenvector 1 2 1 0 1 1 and 1 1 1. Okay, so this is AP and this is P. Then we have to show that P is nothing but a non-singular matrix. See, determinant P is 1, which is not equals to 0, therefore you can say determinant P is, or matrix P is non-singular. Therefore definitely P inverse exists. As P inverse exists, you have to find adjoint P. Adjoint P is this matrix, and do this in your own, because I know you can easily find adjoint of P, because adjoint P is in your syllabus from class 12. Okay, but if you face any problem, you may write in my comment box, I will help you. So here adjoint P equals to this, so P inverse is what? Adjoint P by determinant P. So this is our P inverse. Now see, we have AP equals to this, so multiplying both sides by P inverse from the right, that is AP into P inverse equals to this into P inverse. Okay, so AP into P inverse equals to this AP, and P inverse is this. Then on the right hand side you have to do matrix multiplication, means 2 into 0 plus 0 into minus 1 into 1 plus 1 into 1 is 1, then 2 into 1 2 plus 0 0, then 1 minus 1, that is 1. Okay, that is row into column method, and we know P inverse is I, so A equals to this. So this is A. Okay, so here we actually follow two steps. One is we have to consider P by the help of this vectors 1 2 1 0 1 1 1 1 1, and then do the product or the formula, the definition: ax1 equals to 2x1, ax2 equals to 3x2, and ax3 equals to 1x3. Then consider as AP. Then we have to find P inverse, and multiplying AP from the right with P inverse we will easily find the value of A. So this is the process to find A when eigenvectors and corresponding eigenvalues, or you can say eigenvalues and corresponding eigenvectors are given. So this is all about eigenvalue, eigenvector, characteristic equation, and Cayley-Hamilton theorem. Thank you.